All right, welcome to your first lecture of flipped geometry. Now, I already gave you a little bit of an introduction for how this is going to work, but this is the teaching time. This is the content acquisition time. This is instead of me lecturing you in the classroom. Because this is the first one, I'm just going to take a moment and make sure you know what you're doing. Everything you're going to see on these slides comes from your book. As a matter of fact, this is your publisher's slideshow. I didn't even make it. So if you are worried about writing down everything that you see on these slides, don't stress about that. I would encourage you at this point just to watch the video, read what's on the slides, listen to my explanation, and kind of in your head just go, oh yeah, I understand that. And focus on the auditory and visual acquisition for right now. Then open your book and go through it again and take notes out of your book. That way you will have seen the content twice, and we won't be having a traffic jam in your brain of I've got to read, I've got to write, I've got to listen. Just focus on the listening and understanding the visual verbal cues right now, and then take notes out of your book in just a moment. So let's dive right in. When you think of geometry, you think of points and lines and shapes and objects and spatial relationships, and we'll get to all of that. And geometry is about that. But we're going to use a bunch of notation that you first learned in algebra, a whole bunch in the course of this class. And so we want to review some of the algebra notation that you've already learned. This lecture should not be a learning opportunity for you. Hopefully you watch this and go, oh yeah, I remember that. We did that a couple months ago. So first we're going to review some notation having to do with sets. And we're going to define some terms that hopefully you already have in your head. So first of all, a set is a collection of objects. And it can be physical things, or it can be ideas, or it can be numbers. In algebra, your sets were usually numbers. In geometry, your sets are usually going to be things, points, lines, surfaces, those sorts of things. We're going to just use my living room here. You're in my home. Welcome to my home. And we're going to use this living room as a set many times as an example in the course of this lecture. So we typically denote a set either with a capital letter, and we say set A equals, and then we'll use some fancy brackets, and anything that we list between those brackets is part of that set. Anything we list between those brackets as a member of the set, we can call it a member or we can call it an element. So let's say the set of my living room includes me, and Mrs. Alley's over there, you can't see her, and the entertainment unit that I'm talking to right now, my couch and these pillows and those pictures behind me and all those things. This is all part of the set of my living room, and these are all elements within it. Okay? We can describe an element either by listing the elements, or by stating a rule that determines that these things are in a set, or by using set builder notation. So let me give you some examples. I can list my couch and these pillows and those pictures of my wife and myself and the TV, and I could put a comma between them all, and then I would say if it's on this list, it's in this set. Or I could say set A equals any physical object within my living room. Well, that's the rule. And if you find a physical object in my living room, then it's in that set. And that would be a rule-determined set. Now, going back to algebra, you probably saw rules like every positive integer between 2 and 200. Well, that would be a rule. So if you saw number 63, well, that's part of the set because it's in there. Okay? Or you can use set builder notation. This is a little bit more confusing. We would say that set C equals X such that, this vertical line is read as such that, and then you state a rule. X is a letter in the word complement. So all of those letters are part of the set. Now, there's not that many letters in the word complement, especially when you take out duplicates like the M's and the E's. So if the set is that small, you might as well just list it and put commas. But the example there is set builder notation. Set C equals X such that X, and then you state a rule. And then everything that follows in that rule is a part of the set. All right? Moving on. Let's get to some terminology. That funny-looking E there is a symbol that means element of. And so it looks like an E, and that's on purpose, so that you can remind yourself of what that word means. So if I were to say set A equals, and then a whole bunch of things, and then I were to say, is this thing part of set A? You could look at the set list and say, yes, it is. This object is an element, and put that little symbol of set A. Okay? Now, there's this other symbol that you've seen a whole bunch in your life and didn't necessarily know that it was a mathematical term. The circle with a slash through it means empty set or null set. And what we mean by that is that there's nothing that fits this rule. You've seen that symbol a whole bunch of times in restaurants and public places with a picture of a cigarette in the middle of it. And what that means is that the set of smokers in this area is empty because you can't smoke here, right? So that circle with a slash means no, don't do that. But it also means the people doing this equals 0. There's nobody doing this because it's forbidden. It's taboo, right? You're not allowed to do that here. Some other definitions with regard to sets. If you have two sets, you can compare them a couple of different ways, and here's some of the more common. You could say that the two sets are exactly identical. Now, you would have to have two different names for these sets or it would be a nonsense statement. But let's give you an example of equal sets. If you were to say that there's set A, which is all of the adults in this room, there would be two people in that, myself and my wife. Then you were to say set B is all of the adults in my home. Well, still, two people, myself and my wife, but they're different sets. One is all the adults in this room, and the other one is all the adults in my home. Now, if my wife were to get up and leave the room, but stay in the house, now the sets are different, right? But for the moment, right now, those two sets are equal. They have exactly the same items in it, okay? A subset is a very similar idea, and for the sake of our conversation here in geometry, you really don't need to worry about the difference between a subset and an equal set. Both of them have the same items in them, okay? So just look at the symbol here. The subset looks kind of like the letter S. See that? Looks sort of like the letter S. If we were to fill that in, it would be a letter S, but it also has half of an equal sign underneath it, and that will help you remember a subset is the same thing as an equal set, right, for our purposes. A proper subset, though, is different. A proper subset, something fits inside something else. It's nested within something else. So we could say that one set is our geometry class, and another set is boys in our geometry class. Well, the boys in our geometry class are part of the set of students in our geometry class, but there's fewer of them because we have some precious ladies in there, right? So one set fits within another. That is a proper subset. And notice the symbol is very much like the subset symbol, only there's no half of an equal sign underneath it because it isn't the same thing. Okay? Some other symbols that you're going to be familiar with. You know what an equal sign is? An equal sign with a slash through it means not equal. You've seen that before. If the funny looking E means an element of a set, then an E with a slash through it is not an element of the set. Okay, so adults in my living room does not include Tegan because she is neither an adult nor in my living room right now. Okay, not a subset of. So this is you have two sets, and one of them is not the same thing as the other one, so it's not a subset of. It's also not equal to it. Okay, not a proper subset of. So if we were to say geometry students and my wife's goldfish. Well, my wife's goldfish does not fit within the geometry students. They are not currently studying geometry in goldfish class, so they don't fit within that set, right? They're not a proper subset. All right, let's do an example here. So if set A is the numbers 1, 3, 5, 7, and 9, and set B is the numbers 3 and 7, and set C is x such that x is between 0 and 10, and it is an odd integer. Well, if you think about that rule for a minute, what are the odd integers between 0 and 10? They are 1, 3, 5, 7, and 9. So A and C have the same items in it. It's just written two different ways. All right. So let's determine if the following statements are true or false. Is the set 1 an element of A? Well, if you look at A, here's 1. Here's A. 1 is a part of A. So yes, true. The set 1 is an element of A. Let's look at another example. Here we have the same three sets, right? And we're going to say, is A not a proper subset of C? A is not a proper subset of C, which means A does not fit inside C. Well, C and A are exactly the same thing. It's just that one is written with set builder notation and one is listed out. And so A does not fit inside C. It's the same thing as C. So A is a subset of C, but not a proper subset of C. Okay, so true, while A is a subset of C, it is not a proper subset of C because they're the same thing. A and C are equivalent sets. Okay, one more. Given the same three sets, determine if B is a proper subset of C. Do 3 and 7 meet the rule that it's a odd integer between 0 and 10? Yes, 3 and 7 are both odd integers that are between 0 and 10. Here they are right here in the equivalent way, right? And so this part is true. All of the elements of B are in C, and B itself is not the same thing as C because it doesn't have the other numbers. So it fits inside it. So it is true that B is a proper subset of C. Alrighty. One more. B is a subset of the empty set. B is a subset of the empty set. Well, the empty set is nothing. So is B the same as nothing? No, B has items in it, right? And so false. Neither element of B can be found in an empty set because if it's empty, it doesn't have 3 and 7. Okay? We're going to move on to some more terms. The next term we need to be familiar with is the universal set, and that's properly named. The universal set means everything in the universe, or at least everything that could possibly be in this set. And so the universal set is usually things outside the set. So if the set is my living room, that's the set. The universal set is everything outside the living room, and it includes the stuff in the living room because it's everything in the universe, everything possible. Is the universal set. And we use a capital italicized letter U to indicate the universal set. Equivalent sets are two sets that don't have the same exact items in them, but have the same number of items in them. So let me give you an example here. Adults in my living room, myself and Mrs. Allen. Then I could say that another set is children in their bedroom, and they're currently sleeping. It's late. And so that set and this set have different items in it. I am not a child in their bedroom. I'm an adult in this room. But the adults in this room has 2 items in it. The children in that room has 2 items in it. They are equivalent sets because they both have 2 items in them, although the items are not the same. Okay? So let's look at some pictures here. We have the universal set, and we indicate that with the U and this box drawn around the circle diagrams. And so this box is everything in the universe, you and me and your cat. And set A is something else. Set A contains set B. Set B is within set A. So set B is a proper subset of A, and both of them fit within the universe, the universal set. Here we have another example. We have 2 sets, and both sets have 3 things in it. The set for girls is Heather, Rhonda, and Joy. The set for boys is Jack, Fred, and Ron. And so these 2 sets are equivalent because they have the same number of items in them, although they are not equal because Heather and Jack are not the same thing, praise God. And both of them fit within the universal set. All right, so a union. This is a set function. Up until this point, we've just been talking about what is a set. Now we're going to be letting you do things with the set. So a union is when you take 2 sets and you stick them together, and you make them the same thing. So again, back to my living room. 2 adults here, 2 sleeping children over there. If I were to say, let's take set A, the adults in this room, union set B, the sleeping kids over there, and I were to make this union symbol between them, what I'm meaning is to take this set and put them together, and now the answer to that is my whole family, because now we've got all 4 members of my family represented. And we have a symbol that looks a lot like a letter U that's been pulled to be wider. So be careful when you're doing your homework. The universal set is just an italicized letter U. Draw a U, kind of slanty, and make it look like a U that's just slanty. But the union set is wider. So you've got to be careful with your handwriting that I don't read your work and think A, universal set B, because that would be wrong. I don't know what that is. The widened U is the union symbol. And I'm sorry that they're similar. Go take it up with the ancient Greeks, right? They came up with the system. Okay. Intersection looks like a union symbol that's been flipped upside down. So sometimes people get the union and the intersection confused. The union looks like a U. The intersection does not, because the word intersection does not start with a U, right? Okay, so an intersection is where set A and set B overlap. The union of adults in this room and sleeping children over there is my whole family. The intersection of adults in this room and sleeping children over there is an empty set, because there are no adults sleeping over there. And so that just is one example. An intersection is where two things coincide. So I could say adults in this room and men. Well, the intersection of men and adults in this room is me, because I am both a man. Yes, I know that, even though lots of people in my generation and nation don't. And I am in this room. So that is the intersection of A and B. That's where they overlap. The next idea is a complement, and that doesn't just mean, oh, you look nice today, you don't smell like a dog. That's not just the only way that we mean complement. A complement is something that is not something else. So, adults in this room, your mom and dad do not fit within the set of adults in this room because none of your parents are here right now. And so we could say set A is adults in this room. Complement of A would be everybody except the adults in this room, and your parents would fit into that set, and for that matter, so do you, and so does your cat. It's something that is not part of this set, right? So we use the little apostrophe after the set to say the complement of A. When I learned geometry, we would always read that as not A. The little apostrophe would make us say not. And so you might hear me do that in class because that's just kind of wired into how I learned this. Your book says complement of A. Other people also say not A, right? And that makes sense because there's A and then there's everything else. A and not A. The complement of A is anything that isn't A. Okay? So let's get some examples here. We have set A and set B within the universal set. And if I were to say the union of A and B, then I would have to color in everything in both of those circles. That's the union of A and B within the universal set. Because A and B are both being considered. We're putting them together. That's the union. Here's the intersection of A and B. It's only the things that are in both sets, right? So this might be students at school, and this might be sophomores. And there are sophomores that are not students at school because they're sophomores like at Campbell High School, etc. And so, but sophomores who are also at this school fill in the middle here, and that would be the intersection of A and B. I would only color in this part. Then I could say not A, or the complement of A, and then here's the universe, here's A, and the answer is everything that is not A in the universe. Okay? So that's just some pictures to help you with some of these definitions. Let's look at a couple of examples. If set R is 1, 2, 3, and 4, and set S is 1, 3, 5, and 7, and the universal set is X such that X is a single-digit natural number, that's the universe we're using. Okay, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, find the result of each set operation. So R union S. We're going to take R and we're going to take S and we're going to smash them together. So 1, 2, 3, 4, 5, and 7 would be the answer there. Okay? 1, 2, 3, 4, 5, and 7. Because 6, 8, and 9 that are not part of either R or S are not something that we're going to consider. But everything that's in either R or S, we're going to consider as part of the union of R and S. Let's look at the intersection of R and S. So now here's R and S again. Only the intersection, only where they overlap. They both have 1 and 3, 1 and 3. And so 1 and 3 would be the intersection of R and S. Okay? One more. R, not R, or the complement of R, would be anything that is not R. So here's R. And now I'm looking at 6, 5, 7, 9, and 8, because all of those are part of the universe, but not part of R. And so the answer to that would be 5, 6, 7, 8, 9. Ready? if you have any questions on those, be sure to ask me tomorrow. We will spend some time going through Q&A, okay? Binary operation is just when you take two sets and you do something. You union, you intersect, you complement, you do something to these two sets. A unary operation is applied to one set, like R and then the complement of R. And then a disjoint set are two sets that have nothing in common. So the adults in this room and the dogs at the pound, they don't overlap. There's no adults in this room that are also dogs at the pound. So those two sets are disjoint. They don't touch, they don't overlap, they don't have anything to do with each other, except that I was recently at the pound petting dogs. Okay? That's it. That's the information from 1.1. It actually is a lot of information, and in the last version of the textbook, this was 3 lessons. But in addition 4, they've smashed it all into one. So congratulations. If you feel like you're drinking from a garden hose, you are. We'll go through it tomorrow. We'll answer any questions that come to mind, and you will use these terms a lot for the rest of your career here in geometry, actually, for going forward forever and ever in math. I hope you have a wonderful night, and I'll see you tomorrow. God bless you. Jesus loves you, and so do I.